Hello, good day everyone. At this point, we will now be applying vector valued function to different applications. So we will now be discussing arc length and the curvature. To start with, we're going to discuss the length of the arc. We have defined the length of a plane curve with the parametric equation x equal to f of t and y equal to g of t. So the parametric arc length is equal to L, which is the integral from a to b of the square root of f prime of t squared plus g prime of t squared with respect to t. As the limit of lengths of the inscribed polygons and for the case where f and g are continuous, these are the formulas. So again, the integral from a to b of the derivative of x with respect to t squared plus the derivative of y with respect to t squared with respect to t. The length of the space curve is defined in exactly the same way. Suppose that curve has the vector equation r of t equal to a vector with the components f of t, g of t, and h of t over the interval from a to b, or equivalently, the parametric equations x equal to f of t, y equal to g of t, and z equal to h of t, where f, g, and h are continuous. If the curve is traversed exactly once as t increases from a to b, then it can be shown that its length is L equal to um, the length of the integral from a to b of the square root of f prime squared plus g prime squared plus h prime squared dt. So that would be the integral from a to b of the square root of dx over dt squared plus dy over dt squared plus dz over dt squared with respect to t. Notice that both of the arc length formulas, 1 and 2, can be put into a more compact form. L is equal to the integral from a to b of the magnitude square root of x component plus y component squared plus z component squared dt. Because for plane curves, r of t is equal to f of t plus g of tj. So r prime of t is the magnitude of f prime of t I plus g prime of t j, which is equal to the square root of f prime of t squared plus g prime of t squared. And for space curves, r of t is equal to f of ti plus g of tj plus h of tk. So the magnitude of r prime of t is the magnitude of f prime of t I, g prime of t j, and h prime of t k, equal to the square root of f prime squared plus g prime squared plus h prime squared. Example, find the length of the arc of the circular helix with the vector equation r of t is equal to cosine t I plus sine of t j plus t k from the point 100 to the point 102 pi. So I think it would be one complete revolution in the z direction. So from 0 to 2 pi along z. Taking into consideration that x is 1 and z is and y is 0. So f is cosine t. So f prime is negative sine t. G is sine t. G prime is cosine t. H is t, so H prime is 1. So for the length, it would be the square root of negative sine t squared plus cosine t squared plus 1. So that's the magnitude of the derivative. So that would be square root of 2. So the arc from 100 to 102 pi is described by the parameter interval from 0 to 2 pi. And so, from formula 3, we have the length is the integral from 0 to 2 pi of the magnitude of r prime of t dt, which is square root of 2 dt from 0 to 2 pi. So that would be 2 square root of 2 pi minus 0. So 2 square root of 2 pi units. So take note that sine squared plus cosine squared is 1. Next, a single curve C can be represented by more than one vector function. For instance, a twisted cubic R1 of t is equal to t squared, and t cubed for t is equal to 1 to 2 could also be represented by the function. So if t is e to the u, so t squared is e to the 2u, and t cubed is e to the 3u, where u is from 0 to ln 2, representing e to the u. So e to the 0 is 1 and e to the ln 2 is 2, where the connection between the parameters t and u is given by t is equal to e raised to u. We say that equations 4 and 5 are parametrization of the curve C. If we were to use equation 3 to compute for the length of C using equation 4 and equation 5, we should be getting the same answer. This is because arc length is a geometric property of curve, and hence it is independent of the parametrization used. Let's have the arc length function. Now, we suppose that C is a curve given by the vector function r of t equal to f of ti plus g of tj plus h of tk, where t is from A to B, where r is continuous where r is continuous and C is traversed exactly once as t increases from A to B. We define its arc length function S by S of t is equal to the integral from A to t of r prime of u du, which is the magnitude of dx over du squared plus dy over du squared plus dz over du squared, integral with respect to u. Thus, S of t is the length of the part of C between r of A and r of t. So, in between these two regions. If we differentiate both sides of equation 6 using part 1 of the fundamental theorem of calculus, we obtain ds over dt is equal to the magnitude of r prime of t. It is often used to parameterize a curve with respect to an arc length because arc length arises naturally from the shape of the curve and does not depend on a particular coordinate system or a particular parametrization. If a curve R of t is already given in terms of parameter t and s of t is the arc length function given by equation 6, then we may be able to solve for t as a function of s, t is equal to t of s. Then the curve can be reparametrized in terms of s by substituting for t r is equal to r t of s. Thus, if s is equal to 3, for instance, r of t of 3 is the position vector of the points 3 units of length along the curve from the starting point. Reparametrize the helix r is equal to cosine t I plus sine tj plus tk with respect to the arc length measured from 1, 0, 0 in the direction of increasing t. So we have the initial point 1, 0, 0. X is 1, y is 0, and t is 0. This corresponds to the parameter value of t equal to 0. So when t is 0, so this is the point wherein t is equal to 0, yung 1, 0, 0. Cosine 0 is 1, sine 0 is, so at t equal to 0, cosine 0 is 1, sine 0 is 0, and t equal to 0, so 0. So from the point 1, 0, 0. So the derivative of s with respect to t is the magnitude of the derivative of r of t, which is square root of 2. This was derived earlier. This is the square root of negative sine t squared plus cosine t squared plus 1. So sine squared plus cosine squared is 1 plus 1 is 2. And also, s of s is equal to s of t, which is the integral of the magnitude of r prime of u with respect to u from 0 to t. So it would be the integral from 0 to t of square root of 2 du. So square root of 2, the integral of du is u, so it would be u from 0 to t, so it would be square root of 2t. This is the general parametric function for s. So therefore, t is equal to, so since s is equal to square root of 2t, so t is s over square root of 2. And the required reparametrization is obtained by substituting for t. So r of t of s is equal to cosine t, so cosine s over square root of 2 I plus sine s over square root of 2 j plus s over square root of 2 k. So from t, we reparametrize it in terms of s. Let's now have curvature, the measure of curvature for a given space curve. A parametrization r of t is called smooth on an interval I if r is both continuous and r prime of t is not equal to 0 on I. So it should be continuous and not all the derivatives are 0. A curve is called smooth if it has smooth parametrization. A smooth curve has no sharp corners or cusp. Yung cusp, yung ganyan. So there's no sharp corners or cusps. When the tangent vector turns, it does so continuously. If C is a smooth curve defined by the vector function r, recall that the unit tangent vector t of t is given by the unit tangent. So r prime of t over the magnitude of r prime of t. So from figure 4, you can see that t of t changes direction very slowly when c is fairly straight, but it changes direction more quickly when c bends or twists more sharply. The curvature of c at the given point is a measure of how quickly the curve changes direction at that point. Specifically, we define it to be a magnitude of the rate of change of the unit tangent vector with respect to the arc length. We use arc length so that the curvature will be independent of the parametrization. Because the unit tangent vector has a constant length, only changes in direction contribute to the rate of change of t. So, the curvature kappa of the curve is given by the derivative of t with respect to s. So, the curvature is easier to compute if it is expressed in terms of the parameter t instead of s. So, we apply chain rule. The derivative of t with respect to t is equal to dt over ds times ds over dt. And kappa is um, the magnitude of dt over ds, which is, so we apply chain rule again. So dt over dt over dt times over ds over dt. But ds over dt is equal to r prime of t. So kappa of t is t prime of t, the magnitude of t prime of t over the magnitude of r prime of t. Show that the curvature of a circle of radius a is 1 over a. So we can take the circle. So if we're talking about curvature, yung radius of curvature, so it is the reciprocal of curvature. We can take the circle to have a center at the origin, and then the parametrization is given by r of t is equal to a cosine t I plus a sine t j. So circle. So x squared plus y squared is equal to 1, or x squared plus y. So for this one, um, the radius is a. So we have x squared plus y squared is equal to a squared. So we can have a cosine t squared plus a sine t squared equal to a squared. So x is a cosine t and y is a sine t. So taking its derivative, negative a sine t for a cosine t, and the derivative of sine t is cosine t. So we have a sine. The derivative of a sine t is a cosine t. So for the magnitude of the derivative, so it would be the square root of negative a sine t squared plus a cosine t squared. So we have a squared sine squared t plus a squared cosine squared t. So this would be equal to a squared times sine squared t plus cosine squared t. This is 1. So square root of a squared is a. And so t of t, the unit tangent would be r of t. So a cosine t, negative a sine ti plus a cosine tj divided by a. So we remove a. So the result would be negative sine ti plus cosine tj. So we differentiate this. Derivative of sine is cosine, so negative cosine ti, and the derivative of cosine t is negative sine tj. So this would give t prime, the magnitude of t prime to be equal to 1. The magnitude of t prime is equal to 1 because we will be having cosine t squared plus sine t squared. So it would be 1. So this gives us the unit tangent t prime of t, which is 1, and the magnitude of r prime, which is a. So with that, we have the curvature kappa of t is 1 over a. The result of example 3 shows that small circles have large curvature and large circles have small curvature. In accordance with our intuition, we can see directly from the definition of curvature that the curvature of a straight line is always 0 because the tangent vector is constant. Although Formula 9 can be used in all cases to compute for the curvature, a formula given by the following theorem is often more convenient to apply. The curvature of the curve is given by the vector function r is kappa of t is equal to the magnitude of the cross product between r prime and r double prime divided by the magnitude of r prime cube. So for special case of a plane curve with the equation y equal to f of x, we choose x as a parameter and write r of x equal to x of xi plus f of xj. So r of x is xi plus f of xj. So we differentiate this. The derivative of x is 1. And the derivative of f of x is f prime of x. So differentiating it for the second time, we will be having f double prime of x. So since I cross j is equal to k, and j cross j is 0, so I cross j is k and j cross j is 0, the cross product would be giving a vector perpendicular to the original vectors, and the cross product of a vector to itself is 0. So it follows that r prime cross r double prime is f double prime in the k direction. We also have the magnitude of r prime is, so it would be 1 plus f prime squared. So 1 plus f prime squared. So by definition, kappa or the curvature is equal to f double prime of x divided by 1 plus f prime of x squared raised to 3 over 2. The normal and the binormal vectors. At a given point on a smooth space curve r of t, there are many vectors that are orthogonal to the unit tangent vector t of t. We single out one by observing that because t of t is 1 for all t's, we have t of t dotted to t prime of t equal to 0. So, t prime of t, so the unit tangent, is orthogonal to t of t. Note that t of t itself is not a unit vector. But at any point where kappa is not equal to 0, we can define the principal unit normal vector n of t, or simply the unit normal, to be t prime of t. So we differentiate uh, t of t, so that would be t prime of t, and get the unit normal by dividing it by its magnitude. So the vector b of t, or the binormal vector of t, is the cross product between t of t and n of t. It is perpendicular to both t and n because it is the cross product. So if you have a cross product, it would be perpendicular to the given vectors. Find the unit normal and the binormal vectors for the circular helix r of t equal to cosine ti plus sine of tj plus tk. So the derivative of cosine t is negative sine t, the derivative of sine t is cosine t, and the derivative of t is 1. Getting the magnitude, so this would be square root of negative sine t squared plus cosine t squared plus 1 squared. So this part here is equal to 1 plus 1, so that would be 2. So the magnitude of, or r prime of t in general, r prime of t is square root of 2. So its magnitude is square root of 2, and um, the unit tangent would be r prime of t over the given r prime of t is negative sine t I plus cosine tj plus k. And then we divide it by its magnitude square root of 2. So that is the unit tangent. We differentiate it further. So 1 over square root of 2, the derivative of negative sine, the derivative of negative sine is negative cosine, the derivative of cosine is negative sine, and the derivative of 1 is 0. So the magnitude of this t prime of t would be 1, because it would just be 1 over square root of 2 squared times negative cosine t squared plus negative sine t squared. So that this part would be 1, so it would be 1 over square root of 2. So the unit normal is t prime of t over the magnitude of t prime of t. So it would be 1 half over times negative cosine t I minus sine tj all over 1 over square root of 2. So this would just cancel out. So we have negative cosine ti minus sine tj, or negative cosine t, negative sine t, 0. This shows that the normal vector at any point on the helix is horizontal and points towards the z-axis. So the z-axis is 0. So the unit normal at any point on the helix is horizontal and it points towards the z-axis. The binormal vector is b of t equal to the cross product between t of t and n of t, the unit tangent and the unit normal. Take note that this is the unit normal, negative cosine t, negative sine t, and 0. And the unit tangent is t of t over the magnitude of t of t. So that would be this part alone. Negative sine t, cosine t, and k, or 1. So we get the cross product of this. So ito pala yung unit tangent. So ayan. So this would be 1 over square root of 2. For I, it would be cosine t 1, negative sine t 0, minus j, negative sine t 1, negative cosine t 0, plus k, negative sine t, cosine t, negative cosine t, negative sine t. So everything is multiplied by 1 over square root of 2. So this is 0, and then minus negative, so positive sine t. This is 0, so this is negative j times positive cosine t. So we have negative cosine t. And for the last one, we have sine squared t minus negative cosine squared t. So that is 1. So the binormal is 1 over square root of 2, sine t, negative cosine t, and 1. The plane determined by the normal and binormal vectors n and b at the point P on the curve is called the normal plane of C at P. It consists of all lines that are orthogonal to the tangent vector t. The plane determined by the vectors t and n is called osculating plane of C and P. C at P. The name comes from the Latin osculum, meaning kiss. It is the plane that comes closest to containing part of the curve near P, and for plane curve, the osculating plane is simply the plane that contains the curve. The circle of curvature, or the osculating circle of C at P, is the circle in the osculating plane that passes through P with the radius 1 over A, and the center of the distance from P along the vector n, and the center of the distance is called the center of curvature of C at P. We can think of a circle of curvature as the circle that best describes how C behaves near P. It shares the same length, same tangent, normal, and curvature at P. So we summarize here the formulas for unit tangent, unit normal, binormal vectors, and curvature. So the unit tangent is r prime of t over the magnitude of r prime of t. The unit normal is t prime of t over the magnitude of t prime of t. The binormal vector t, b of t, is equal to the cross product between tangent and normal, unit tangent and unit normal, and the curvature is the magnitude of dt over ds, which can be simplified as r prime cross r double prime over r prime cube, magnitudes only. So thank you for watching, and see you in class.